Hi, welcome back to Mechanics and Control of Robotic Manipulator. Last few classes what we have seen is how to derive a dynamic model of a robotic manipulator, in specific serial manipulator. We have seen two methods. So, these even Matlab method, or you can say using Matlab how to derive equation of motion also we have seen. This particular class or this particular lecture we are going to talk about how to do a dynamic simulation. So, whatever we derive that equation how we can use for a dynamic simulation model. So, in the sense we are actually like trying to see basically like you can say the equation of motion we are taking and trying to do the forward dynamics in this particular lecture. So, for that we need to have some numerical integration method. So, here we are going to talk about Euler integration method, that would be very simple. It is a first order integration method that we can use. If you necessary or you feel like it is necessary, even we can use second order or fourth order, you can say numerical integration methods. But here we are going to use the simple first order, which is what we call Euler integration method. Then we will take one simple example and we will see how that example can be ported in Matlab, and based on that how we can actually like do the dynamic simulation along with what you call motion animation. So, this is all what we are trying to cover. In that sense, the generalized you can say equation of motion of a robotic manipulator can be written in this form. Okay. So, this equation we can modify for a forward dynamics, although we are doing in a forward dynamics, in the sense what we know the tau is known and we are trying to find out what is the motion. In that sense, we will start with the initial stage. Initially, the you call system variable called q dot would be known, then tau is known, then how we can actually like get q double dot. This is what we are trying to do. So, for that we are actually like calling this is a dynamic simulation model. We are writing everything in acceleration form. The sense, so q double dot can be written in this simple equation. Okay. So, now you can see here the initial condition q dot and the input tau are known, and the frictional quantity, gravity vector and all other vectors can be found based on that. If we even write this in a you can say you call, even if we draw in a block diagram base, it is very clear, but now we will actually like do it in Matlab. In the next lecture we will see in a block diagram approach. So, in the sense the Matlab case we need to write everything in a code form. So, for doing the numerical integration we will try to use the Euler method. So, how we can actually get the Euler method by you can say demonstrating in this particular plot. So, you can see like here that x of t and time we have actually like achieved here in a plot, where time is the independent variable and the x of t is the dependent variable. So, right now the x of t is given in this particular polynomial. Okay. So, this particular curve. So, now what I am trying to take? I am trying to take as a random ti point. Okay. So, in the sense first instant I am taking. So, what is the corresponding value I call x of I? So, I am taking another step which is we call ti plus 1. So, that would be correspond to you can say x of or xi plus 1. Now, although the curve is actually like somewhat curved, in the sense it is not straight line, but I am trying to make a straight line. Okay. You can see in a green line. So, where xi and xi plus 1 it is connecting. So, now if we see the straight line, what would be the slope? The slope would be x dot of I. That x dot of I, how I can write? X of I plus 1 or xi plus 1 minus xi whole divided by ti plus 1 minus ti, right. So, this is the way we can write. So, now based on the slope one can easily find, if I know x of I and I know x dot of I, and if I know what is the time step I am going to consider, then I can actually like find xi plus 1. So, in the sense this equation what I have written I can rewrite. So, x dot of I multiply with this we call time step, and then I can actually like rewrite this equation. In the sense I consider this as a delta t. So, then you can see x dot of I into delta t plus x of I is equal to xi plus 1, right. So, this is what we are actually like going to call as a numerical integration, that to like Euler's method. So, in the sense this equation is actually like going to use hereafter in the dynamic simulation for our robotic manipulator. So, now if that is the case, how I can write in a generalized form in robotic manipulator? Here there are two things will come, because the robotic system is actually like the equation of motion written in second order equation. In the sense, so q dot can be obtained by taking q double dot as the input, right. Similarly, like a q, we can actually like get it from q dot. So in that sense, this is straightforward from the Euler integration, but this we can rewrite in the way, right. So we know equation of motion for a simple particle, where we call you can say v equal to u plus at and s equal to s naught plus ut plus half at squared. The same way here, this is actually like equivalent to what you call the velocity relation. So in the sense, q dot I plus 1 is the next one. So that can be obtained from the q dot I plus q double dot of I into delta t. So right now we want to go with the position, then you can see like it depends on, you can say, initial velocity, initial position and initial acceleration at all. So in that sense, what we can rewrite this equation. So this is further we are differentiating, okay. So that is what we are actually like trying to do. So now this is integrating it. So if we integrate, what we get, this is actually going to be q I plus 1 and this is actually going to be q I, and this will get something actually like addition. Why? Because this is going to give two set of equation. So that is what we have actually like written, okay. So in the sense, you can see the q dot easily we can obtain. So once we obtain the q dot, we can actually like go to q. So that is the way we can actually like proceed. So if that is the case, how we can actually like take it to a Matlab, you can say, simulation. For that, we will take one of the simplest example which all studied so far in all the, you can say, constraint. For example, you talk about velocity or you talk about equation of motion, we have taken planar to our serial manipulator, right. The same example we will take. So what we have, so m of q is known. So then other effect v q comma q dot is known, and g of, you can say, f of q comma q dot also known, and g of q is known. In the sense, all, you can say, 4 subcomponents are known. So now if I know tau, how can I actually like get this with the initial condition? Because this is actually like ordinary differential equation. For solving ordinary differential equation, you need one of the boundary condition, here we call initial condition. If you know initial condition and input, then you can solve this particular equation. So that is what we are trying to do. For that, we are taking actually like simulation code. So we are again taking it, everything we are making it clear, and sometime we are making a plot. So that's why we are closing all the figure window and clearing the command history, so that we can understand what was the error command or what is the output. Then what we are going, since it is having a several step, first we need to define the integration parameter. So here we are doing Euler integration. Euler integration is a simple first order system. So the dt is what equivalent to delta t, which is nothing but a step size. Here I have taken as a 10 millisecond, it need not to be, but we have taken 10 millisecond. Further, we need to see what simulation range you want to run this particular Matlab code. So that is what I call total simulation time, which is I have written as Ts. Then this is going to actually like a propagate from 0 to Ts with the interval of delta t. In the sense, I am defining the time span, which is starting t, starting from 0 to Ts with the interval of, you can say, our step size of dt here, okay. So this is the first case, we have defined the simulation parameter. Once we know the simulation parameter, then we can go to the system. Then we are talking about the system parameter. Since it's a 2R serial manipulator, the 2 in plane, so then we are assuming that it's a vertical planar. So the G we define as 9.81, then your link length A1 and A2 defined, and your masses of link 1 and link 2 we define. Further, we are actually like taking in the non-rigid body effect. So in that sense, the frictional coefficients, where the viscous friction and the Coulomb friction we are actually considering. So the C1 and C2 I assume to be 0. It can be considered any Coulomb friction factors, but usually we assume that it's a viscous friction. So that's why B1 and B2 are non-zero value. So once you obtain the system parameter, what we need to do, because we are trying to do the system integration, or you can say the state integration, or in the other way around we can call numerical integration. For that, one important step is your initial condition should be known. So we are actually like defining the initial condition. So here the system states are actually like two. One is joint position, the other one is joint velocity. So the joint velocity I am calling q dot, q underscore dot, and the joint position I am calling q. So q is equivalent to theta 1 and theta 2. So q dot is equivalent to so theta 1 dot and theta 2 dot. So right now we assume both are actually like zeros. The sense theta 1 and theta 2 are 0 and theta 1 dot and theta 2 dot also 0. Okay. So once we all done, what else we need to do? We can start the numerical integration. Since it is actually like iteration, because it is starting from time step t equal to 0 to ts as you can say stage by stage as a propagation. So better we have to use one of the loop. So simplest loop which we can use in Matlab is for. So I am using a for loop where it start as the iteration or loop count as I, which start from 1 to you can say length of t. So here length of t is actually like so 0 to ts how much it comes. In this case it is actually like 1001. Okay. So then I am calling like theta 1 and theta 2 is your system state. So here the system state the joint position we have defined as q vector. So the q vector first term equivalent to theta 1 and the second term equivalent to theta 2, but this q vector is actually like going to propagate. So that's why the ith instant equivalent to theta 1 and theta 2. The similar sense q underscore dot would give theta 1 dot and theta 2 dot. So that is equivalent to so theta 1 dot as q underscore dot of 1 comma I and 2 comma I is theta 2 dot. So once you define what you can actually like do, you can actually like start making what you call your individual components. So we can start with the inertia matrix. So you can actually see the inertia matrix we can write as you can say 4 component because it's a 2 cross 2. So all component I can actually like write here. So which start from m11 to m22. So there are 4 terms. So already a1, a2 we defined and theta 1, theta 2 also we defined, which is going to be propagate, and m1 and m2 are constant. So in the sense we can find the inertia matrix. Once we know the inertia matrix, what we can do? We can do the other vector which we call other effects here. So which is equivalent to v of q comma q dot. So this is also like it is nothing but centripetal and you call Coriolis effect that can be given it as this. So then we can go to the gravity effect. Finally you can come with the frictional effect. So although C1 and C2 are 0, but I make it as a generalized one. So in that sense C1 and C2 can be non-zero also. So then you can actually like see what you have to do. Now you have to give an input. So the input vector here I call tau 1 and tau 2 as 0. So then you can ask what you want to actually like expect here. Even you assume that theta 1 and theta 2 are 0, it is actually like this extended position, because our frame arrangement where theta 1 is actually like parallel to x axis and theta 2 equal to 0 means that is again parallel to x1, in the sense it is actually like just extended position. So now there is a gravity is there. Even if I put tau 1 and tau 2 0 and I introduce the friction, what happened? This will actually like come down and swing and it gets settled. That I want to simulate. Okay. Later on I can actually give some tau 1 and tau 2 as the input and see. So now what we need to do? We have to find the q double dot term, which is what we call acceleration vector, that is inverse of m into tau minus v of q comma q dot plus the frictional component plus gravitational component. These all we have actually like used whatever the equation we have written in the previous slide. So then once you know q double dot, what we can do? We can actually like propagate the velocity. So in the sense q underscore dot of I plus 1 we can do, so that we can actually like do it with a simple Euler integration. Then we can go to the position propagation. So with that actually like this would be end. Okay. So here actually like this is q dot, so where you can say comma I, that is what the case. So whatever it is coming, that is what, but it is multiplied with the delta t squared. So that we can actually see in the Matlab code. Then the numerical integration is the end. So what exactly we expect? We want to actually like see what is the outcome once you run this program. So I can actually like plot the positional information along with the time, in the sense the time trend or time history of the you can say joint position I can see. So which is actually like converged to some position, right, that I can see. But in order to see more intuitive way, so then better we can do the animation. the animation part we can do. Here I assume that this is origin, then 1 and 2 you can say body case. So this is the way we will explain. I will explain this into the Matlab code, then that would be very clear to you. Okay. So this is the Matlab code which we were actually like seen in the slide. So you can see that the dynamic simulation of a RR planar robot we have done. So this is what main, and these all we have given. So right now we assume that all frictional coefficients are 0, and here I have actually like assumed the gravity is actually like vertically down. That's why I modified as actually like 9.81 instead of minus 9.81, because when I derived, I have actually like derived opposite direction. So that is the case. I have actually like modified this. Why I did, I will actually show you once the simulation done. So you can see these all. Okay. So this is the simulation animation part. So you can see like here I am calculating the first you can say link end, which I call x1 and x2. You can actually like recall in the slide also the j of x1 comma x2 x1 comma y1 and j of x2 comma y2. That is what we have actually like written it here. So now if I start from origin, then 1 and 2. So if I actually like make as a line diagram with a marker that look like a manipulator. So better I will run the simulation, I will explain later on. So now what we have given, the 0 initial condition, right? So you can see that this is 0 initial condition in the sense, so q vector and q dot vector are zeros, and further the tau 1 and tau 2 also 0, although I have put it some value, but the equivalent is actually like 0. Okay. So now if I run this, so you can see like, so due to the gravity the manipulator will start oscillate as a double pendulum. We can see that. Okay. So now you can see, right. So it is very clear now. So it is a red you can say line connected. This is what you call as you can say 2R serial manipulator. So this is the origin, this is x1 y1 and this is x2 y2, and now due to the gravity it is actually like swinging like as a double pendulum, and it is actually like ended. So now if you see the plotting option also, you can see that initially it is start from 0, but due to the gravity it is actually like start oscillate, and it end with what you call 0 for theta 2, because theta 1 and theta 2 are collinear, that is why theta 2 is 0, and theta 1 is minus 1.57 something, which is equivalent to pi by 2, which is nothing but in degrees it is 90 degree. So that is what we have actually like seen. So now there is one question will come. So if I take this is minus 9.81, it will show that is opposite direction. Okay. Why? Because we assume that the gravity is vertically down and you choose the direction is minus, so then it is actually like swinging up and hold it. It is not going to happen because the gravity is eventually pulled down. Okay. So I just to show it here, you can see like this is actually like going up. This is not going to happen in real, right? So that is why we have actually changed the direction, because this is what we have taken as a syntax. What direction we have taken, accordingly it is actually like coming up. So in the gravity vector we have actually like assume it is vertically down, so that is why it is actually like opposite direction. I hope now you are clear why GS actually like consider that way. So now in order to understand more and more clear, you can actually like change the frictional component. For example, there is no Coulomb friction of the first joint. So you can see like that what you call oscillation is actually like completely different. Okay. So you can actually like see it, right. It is something like it is not getting settled, because the viscous friction only there, it is taking a long time to settle, that you can actually like feel it. But if the Coulomb friction is there, it is actually like one kind of static, it is making further because it is a constant force, right, acting opposite direction. So that is what you can actually like see it. So now I assume that, so there is you can say both Coulomb frictions are 0. Okay. So I am actually like checking it with gravity is pulling down. So now you can actually like see that it is further, it is taking time, even the 20 second or whatever I have given, that duration it is not sufficient to get settled. You can actually like see, right. So now if I eliminate the friction, you will feel completely different phenomena. What different phenomena? It will get some kind of startup energy. You can see it is actually like supposed to be marginally stable, right. Whether that marginally stable system, in the sense it would be a continuous oscillation with the equal interval, that is happening or not, you can actually like see it. Okay. So you can see, right, you now you would have seen, right, it is actually like getting oscillation, right. It is completely not acceptable in real time. So if you leave it, the system will not propagate. So now one can see why this is happening. It is very simple, because we have done with a simple numerical integration. So this particular phenomena is not able to observe with a simple Euler integration. Further, there is no friction. So because of that, what happened, it is actually like the second bar which is actually like making a swing up, or you can say it is producing kind of energy. So theoretically it is not justified, because so as per the energy conservation principle, it cannot be done this way, right. So that's why we are actually like introduce this friction, and that way we can actually like get it more, you can say, realistic result. Okay. So now even the Coulomb friction you want to add or not, it is up to you. But now if I actually like take the gravity vector 0, in the sense I said that there is no gravity at all, in the sense I put g equal to 0, then what one can expect, it would be remain the same place, right. That's supposed to be, yes, that is matching, right, because you have tau 1 and tau 2 are 0, and you don't have any input or any external impact or any external efforts. So obviously the system will remain as same. So now if you provide input what you call tau 1 and tau 2, just for demonstrating, I assume that the tau 1 is actually like 0.1 Newton meter. So what one can expect, so the second system will remain same? No, because there is a interactive effect that you can actually like see. Okay. So I'll actually like, you can, it is very slow speed, right, you can actually like not able to realize that explicitly. So I will give that unit is slightly different, because we made it actually like very slow. So I'll just stop once it is actually like done. You can see, right, it is actually like moving, but here you can actually like see this particular term, the theta 2 dot is not generating at all, right. So theta 2 dot is actually like not generating, that's why you are actually like not getting it, but theta 1 dot is generating, right. So that may actually like influence some effort. So that effort I want to see. So for that, what I am actually like trying to see, even if I put this equal to 0, but I am giving a continuous signal which is actually like varying in this manner, because we have a very strong frictional, right. So that's why it is actually like doing it that way. So now you can actually like see the friction is there, that 2 Coulomb friction is there. It is actually like oscillating, but the friction is actually like avoiding, because it is actually like very strong. So I'll just make it, you can see it is oscillating, it is not so visible. I'll make it what you call that Coulomb friction as 0. Okay. So then I'll actually like make it. So here the Coulomb friction is 0, because the Coulomb friction is constant force, right, only the direction is getting changed based on the rotation. So now you can actually like see, so this is actually like start oscillating, right, with the given input, and not only this oscillating, the second bar also getting oscillate because of the coupling effect, right. So that is what I want to show here. So now you can actually like see the same way, if you apply even input, so you can actually like find a little more, you can say, clarity result. So now you can see that this is oscillating and this is also like getting oscillate, right. I just want to show that in more clarity. So I'll just give, this is also one input. Okay. And here I am just adding one more. Okay. So I'm just holding on, then I'm just plotting, you can say. So I'll just say that this is x equal to, I'll just put it x of I equal to x2 and y of I equal to y2. Okay. So this I did not do it earlier. So now you can actually like see this. So I just corrected this. So now I am actually like plotting. So x of 1 to I. Okay. So, y of 1 to I, in the sense that time history would be very clear. So, we can actually like see that. So, for that only I am just doing it here. So, you can see the profile also continuous. Okay. So, now I am actually like holding you can say off itself. So, now I am just running this. You can see the time history of the total thing in 2D plot. Okay. So, I hope that is, I will just check it. Okay, this is okay. So, once that is done, I will actually like run it here. I just wanted to show one addition. So, with that we can actually like end this. So, I want to show the time history, you can see, right. So, this is what I just wanted to show, how the profile is actually like varying. So, this gives actually like how that link is actually like getting into connected. So, even you want to actually like make it much more clear. So, even actually like you want to actually like make it much more clear. So, you can actually like start from 0, or you just wanted to plot only those corresponding points, you can still do it. So, that we can actually like do it in the Simulink based simulation. Okay. So, in the sense the block diagram base. So, right now you can see this part is just a plotting option. So, where you can actually like see that the q of 1 and 2 we have plotted. I hope now this is actually like going to give a clarity how to do the dynamic simulation and how to change the parameter. Now, you can change your mass and you can change the link length, and you can actually change the frictional coefficient, and then you can actually get some kind of idea what your system all about. Okay, how your system will behave, all those things you can find it. So, with that I am ending this particular lecture. In the next lecture we will see the same thing in a block diagram basis, and followed with one important phenomena called trajectory generation, because we are trying to do the inverse dynamics without even controller. So, after that we will go to the motion controller. Okay. So, in that sense, thank you and see you then. Bye. Take care.